This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 3, Lesson 4, Multistage and Cascade Systems. When the pressure lift from evaporator to condenser is too big for a single compressor, we split it across two stages with a flash intercooler in between. The handbook draws this as the dual compression, dual expansion cycle and prints its COP. We'll read the cycle, set the intermediate pressure with the equal ratio rule, work one number, then name the cascade arrangement. Concept 1. Why stage the compression? A deep freeze evaporator and a warm condenser can demand a pressure ratio far past what one compressor handles well. Discharge runs hot and volumetric efficiency drops. So split the lift into a low stage and a high stage, each with a smaller ratio, and put a flash intercooler between them to desuperheat the low stage discharge and flash the liquid at an intermediate pressure. The handbook draws this as the dual compression, dual expansion cycle. Concept 2. Read the cycle. Start at the evaporator, state 8 to 5, then the low stage compressor, 5 to 6. That discharge enters the flash intercooler, and saturated vapor leaves it as state 1 into the high stage compressor, 1 to 2. Then the condenser, 2 to 3. High-pressure liquid drops through expansion valve 2 into the intercooler, and intercooler liquid drops through expansion valve 1 back to the evaporator. 1 refrigerant, 3 pressure levels. Setup. The two-stage COP. Refrigerating COP is the evaporator effect, H5 minus H8, over the sum of both compressor works. Heating COP swaps the numerator for the condenser rejection, H2 minus H3. The table maps each enthalpy difference to its role: evaporator load, low stage work in Compressor II, high stage work in Compressor I, and condenser rejection. Both works sit in the denominator. Concept 3. The intermediate pressure. The handbook's multi-stage rule is that total work is minimized when every stage carries the same compression ratio. Set the low stage ratio equal to the high stage ratio, and the intermediate pressure falls out as the geometric mean of the evaporator and condenser pressures. Each stage then sees the same ratio, the square root of the overall ratio. Work in absolute pressures. Solve. Evaporator at 10 pSAA absolute. Condenser at 250. An overall ratio of 25, far too much for one compressor. The intermediate pressure is the geometric mean, root of 10 times 250, root of 2500, 50 pSAA. Check it the other way. Pi squared equals the product, so Pi is 50 again. Each stage now carries a ratio of 5, and 5 squared is the overall 25. Evenly split, minimum total work. Concept 4. Cascade systems. A two-stage cycle uses one refrigerant across both stages. A cascade uses two separate loops, each with its own refrigerant and compressor, joined at a cascade heat exchanger, where the low loops condenser is the high loops evaporator. It reaches very low temperatures no single refrigerant covers well. The handbook draws only the single refrigerant two-stage cycle, so cascade is a named concept, nothing to cite. Traps. 5 ways this bites. 1. The ratio rule uses absolute pressures, never gauge. 2. Compressor II is the low stage taking evaporator vapor. Compressor I is the high stage, its work H2 minus H1. 3. The refrigerating effect is H5 minus H8, not the single stage H1 minus H4. 4. Two-stage is one refrigerant, cascade is two separate loops, only 2 stages printed. 5. The COP denominator sums both compressor works, not one. Quick recall. The cycle is dual compression, dual expansion with a flash intercooler. Refrigerating COP is the evaporator effect over the sum of both works. Total work is least when the stages share a ratio, which sets the intermediate pressure to the geometric mean. The handbook even sizes intermediate and low stage piping. Cascade uses 2 separate refrigerant loops, joined by a heat exchanger, a named concept. Golden rule. 2-stage is 1 refrigerant, cascade is 2, and pressures are absolute. Next up, Lesson 5, Absorption Refrigeration. There we drop the mechanical compressor entirely and let heat drive the cycle. We'll build the single effect diagram, generator, condenser, evaporator, absorber, solution heat exchanger, and pump. Then the ideal COP chain, lift and drop, and the minimum generator temperature. Everything's at PEPrepEngine.com. Cheat sheet, work solution, and a quiz attached here. If the course helps, subscribe.
The full study guide with every equation and common exam trap is free at PEPrepEngine.com, link in the description. Structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.